So based on what we just got right here, if we now summarize something, so we went through all the work, but from spherical coordinates to rectangular coordinates, here are some formulas. Now we've come up with all the pieces. That is, let's say you're given the value of rho and phi and theta. Okay, somebody gives you rho, phi, theta. They give you the three numbers in spherical coordinates, and you wanna, because spherical coordinates is still new, you wanna understand it in rectangular coordinates x, y, z. How do you do that? Well, based on knowing rho, phi, and theta, how do you get x? It's up here, right? So let's just summarize, what we have by saying, what you do is you'll say x is given by rho, a number you were given, times sine phi times cosine of theta. And then y would be given as rho sine phi times sine of theta. And then lastly, how do you get z? Well, that's actually up here already. Z is just going to be rho times cosine of phi. In addition to this, so that's how you convert from spherical coordinates to rectangular coordinates. But in addition, there are quite a number of other equations that we've developed along the way, and they're all useful at different times. So let's just inventory all of them. We also have that tangent of theta is equal to y over x. We also have r squared is equal to x squared plus y squared. And we had these before, right? These are just standard things in polar coordinates, so they would still apply to cylindrical coordinates, and in as much as the coordinate names are basically different in spherical, with the exception of theta, and at least theta means the same thing in both. So we can hold on to all these equations. There's no worry about some kind of contradiction, or this meaning this over here and that meaning that over there. So anytime you see a variable, its role is always the same no matter what. We also had rho squared is equal to x squared plus y squared plus z squared. And so you can combine these two, replace the x squared plus y squared, and you can get an equation like this, right? Rho squared is equal to r squared plus z squared. So if it's helpful to you, why not just have that equation? It's just another thing that's true. In addition, from way back over here, I'd like to just copy paste that we had these two equations. So we had copy, paste. We also have sine of phi is equal to r over rho, and cosine of phi is equal to z over rho. So I think the point is, yeah, these equations are nice, but that's what you do if you're going from rho, phi, and theta to x, y, and z. If you're doing some other things, you may need some of the other equations in here as well. Now, let's take a moment to talk about a spherical rectangle. Okay, this wording's a little funny, but what I mean to say is there's a sphere here, let's just say, and let's say that the sphere is slightly thickened. So I want two slightly different values of rho, right? So like rho old and rho new, and those numbers should be very close to each other. And then let's say you slice so that you have just a little bit. So we just want a little bit of rho, we want a little bit of theta, and we want a little bit of phi. So a little bit of theta is going to actually end up looking like this, and a little bit of phi, well, remember that's the angle from the positive z-axis. So you actually get like a thing that looks like this. So oh yeah, it should be a little thicker just due to the rho old versus rho new. So it's hard to draw this. I apologize, but what this basically is just like a little square, and it's not quite a square, but it's like the closest approximation to a square of, let's say, an orange peel. So you've got the whole orange, but I don't want all the inside. The peel is a good example. The peel part is a good example of delta, which is it? Delta rho, yeah? Just two nearby values of straight line distance to the origin. And then chopping, I guess, this way would be so that distance here would be your delta theta, and then the distance this way would be your delta phi. Okay, so it'd be almost like if you could make some cuts of an orange using a knife, and your knife does not make any turns. You just slice, slice, and so on, and you get a little piece out of an orange. That would be this little, this little piece here is what we're trying to talk about. Okay. So we're not going to work through the details of what's the volume of this. It's messy. Okay. I'll just say that the volume. We're just going to say it. Okay. We're not going to run through it. It happens to be rho sub I. So whatever the value of rho is for this specific subinterval. Okay, so usually calculus books have a star there for that. That number squared, again, we're not going through y, times sine of phi sub k star, so specific value of sine of phi, then delta rho, let's make that look like a rho, delta rho times delta theta times delta phi. Okay, we're not going to go through why it looks like this. It is really messy geometry. And the point is then dv, which we had previously expressed as something like dx times dy times dz, right? This in rectangular coordinates, and there's actually 5 other ways of doing this, right? There's 6 ways total. Now, we had also seen that this was r dz dr d theta. This is the kind of thing we'd write down if we were in cylindrical coordinates. The point is now we also have dv based on what we see here is going to be written also rho squared sine of phi d rho d theta d phi. So what's all this extra stuff here? It really appears for the same reason that r appeared there. We're not going to really go into the details. We will come up with an explanation for this a little bit later that's rather different. But for now, we're just going to take that this is here for the same reason that r is there. And why is it specifically this? We're not going to go through it. I will just comment that right here, this is putting rho and then theta and then phi in that order. This is the usual order of integration. If you have a good reason to not follow the usual order, then go for it. But I think we'll stick as much as possible to following the usual order of integration. If you switch up the order and you're convinced based on the shape you're integrating over it's not going to matter, or that another order is easier to think about or whatever, then go for it.